عليكم السلام.
عليكم السلام ورحمة.
Before we start, do you have any questions, any comments, or any concerns? Anything? Anyone?
Yes, Doctor. We have next class quiz, isn't it?
Yes.
Can we delay it a little bit? Because
الفكرة يا دكتور انه معلش يا عبد
Wednesday.
الرحيم.
اوكي
كمل.
go ahead.
خلاص كمل لي انت.
عندنا يوم الربوع شو اسمه ميجر ال 440 الاي سي اس.
واغلب الطلاب يعني في الكونسنتريشن منزلين المادتين هذه مع بعض، فحيكون شوية ضغط عارف.
ماشي. طيب هو الأحد.
اوكي.
Yeah, it will be better, Doctor.
طيب. Okay.
Wait,
So
the quiz?
quiz. Yeah.
Sorry, I can't do Sunday. I have a midterm exam.
Which midterm?
COE 444. Sir, this Monday is actually good for me.
Monday we don't have a class on Monday.
طيب should it be in the class? Can we take it in another time? Not in the class.
It's up to you. And I usually prefer it to be in the class. I know, and you have limited hours in the day. If you wanted to have if you want to have it like after the like outside the class, that is fine. ما عندي مشكلة.
طب what about if we choose next Monday?
Next Monday, I have ICS 324.
Dude, you always have.
Yeah. This Wednesday we have the 440. Next week Sunday 444. Monday 324, and then Thursday 426.
Okay, guys. See, look, you know, these weeks we always have something, right?
Yeah.
So this is a quiz, okay? So, it's not a midterm exam. So, we cannot avoid conflicts with midterm exams and other quizzes.
Sure.
Like
the original time you gave of Tuesday is good for me. The original time you said Tuesday, this Tuesday, the day after tomorrow.
Right. So are you in the concentration? Are you in the concentration area?
Yeah, CyberSec.
CyberSec. Right.
Yep.
So, well, I would say Tuesday is fine because we agreed on Tuesday last time. Nobody had any issue, so I think we should stick with it. So I'm fine with delaying it. I don't have any problems. But if somebody, is had a concern, then we just leave it as is. It's fine. That is.
Yeah, that's good.
So we'll have it in Tuesday. Since the midterm is in Wednesday, I'm sorry to say that I don't want to be this kind of professor. You have to manage your time and so on. But this is, like really, what I'm trying to say here is that we are not lobbying against you, like as instructors. And I've been there, like as a student, and I know all this kind of pressure. But this is a natural thing because we cannot avoid or we cannot have slotted exam between all the courses and like a schedule that fits every one of you. So we have like each class is kind of running independent from other classes, and we have module and sections to finish, and like once we are finished with the previous module, we have to take a quiz or a homework, right? And I from my side, I always give you one week ahead, right? So I gave you, I told you last Tuesday that we're gonna have a quiz Tuesday, and I'm always fine. I'm always up to delaying. Like I'm with you guys, but sometimes it's we have to take it. So if I think we'll just keep it for Tuesday because I know these midterm exams, but this is a period of midterm exams. In this week and the next week, okay. So I think I'll use my authority here and I'll keep it on Tuesday, okay. But what I promise you is that it's gonna be straightforward. It's not gonna be that hard. So during or next Tuesday, I will take again 10 to 15 minutes as a review. Okay, just like what we used to do whenever we finish the model, right? And I promise you, if you pay attention in the first 10 to 15 minutes or maybe 20 minutes, you'll be able to do well in the exam, in the quiz. Make sense? So even if you don't study, if you like care enough to like pay attention during the review, you will do well in the quiz. So just to minimize the pressure on you, like preparing for the quiz as well as the midterm exam. Okay, agree?
Doctor?
Yes.
Wasn't it on Thursday in the last announcement?
Thursday is the midterm exam. Not this Thursday, the Thursday after, 29th of October. Right?
Oh, okay. You're talking about the quiz?
The quiz, yeah.
Oh.
Okay. And you see, I'm always up to delaying the quizzes and homeworks. But if I delay this quiz, you will not take it next week, and because we have the midterm exam, and the week after will be a little bit late because we're gonna start new topic. And I promise you, we're gonna take at least 5 quizzes. Each will have 2%. That will cut 10%. And as extra help, I will give you one more quiz, just in case you did like one didn't go well in one of the quizzes, so you can replace it with that extra quiz, right? So like we have kind of a little bit of tight timeline in terms of quizzes. And as of the homework, I have it ready. It has some programming assignment, but very light one, not that difficult. But I'm delaying it because next class, inshallah, I'm gonna go over kind of a tutorial, right? So I'm using this Jupyter Notebook, Python. I will show you how we're gonna construct a database, how to, like kind of practical example. How can we actually execute a Laplacian mechanism? And then I'll ask you, for the homework, I'm gonna ask you a task based on the code that I'm gonna go over. Make sense? So that's why I'm delaying the, releasing the homework until I go over the code, and then I'll go over the homework with you. Okay? So.
Okay, sounds good.
Quiz on Tuesday?
Okay, thank you, Doctor.
Yeah, no problem. Right. So let's move on. So as I said, so this is kind of what is the plan for this week, and hopefully next week with the midterm exam. So Tuesday we have a quiz number 3. And the midterm exam will be Thursday, 29th. I wanted to say I'm gonna book a room, but it's gonna be online. So it's gonna be, I think it's from, what time was it? Did we agree on the time? 6 to 8, right? Okay. I guess. Anyway, so I'll most likely gonna be on Blackboard. It's gonna be timed exam. Okay. Homework 2 will be released, inshallah, within this week, but I'll give you enough time way after, like the midterm exam, so that you can take a little bit of, you can breathe, and then you can, start working it. But it's not gonna be that difficult, inshallah. Right. So let's move on. So today, inshallah, we're gonna, like kind of wrap up the discussion on the slides that we started last time, and then we're gonna start another slides where we're gonna talk about another type of another mechanism to achieve differential privacy, as well as some light application, right? So I'm not gonna ask you to memorize and know the details of how apply differential privacy in these use cases. It's just kind of for your to make the course a little bit practical and for your information. Okay. So this is the outline. So after we define the privacy, we have a formal definition of differential privacy, right? We said that. So this is the kind of the formal definition. Sorry. So this is the formal definition, and we said that, like in terms of privacy budget, epsilon is the parameter that kind of control the amount of noise and the privacy that we are targeting in the application, and we said that small value of epsilon, right, will give us a better privacy, right? So and you can basically convince yourself, so because if we have an epsilon almost equal to 0, right, then e to the power epsilon is equal to 1, then this probability is equal to this probability, right? And then basically we are making the kind of the adversary a little bit kind of confused, because these probability are indistinguishable. So we are perfectly achieving the objective of differential privacy, which is, you know, like having the two probabilities to be indistinguishable, or you know, like not that different. Make sense? But we said that, of course, epsilon has to be greater than 0, because epsilon is equal to 0 is almost it's almost like you know, not I wouldn't say impossible, but it would be it would add a lot of noise, because we consider what is called the Laplacian mechanism, right? And the Laplacian mechanism basically is I'll skip this global sensitivity for the time being. The Laplacian mechanism basically, it says that if we have a mechanism, and this mechanism will add noise, right, based on that is drawn from a Laplace distribution that looks like this, right? And so this Laplace distribution, it has a formula, closed formula, and it's proportional to this value, right? So we said that B is the variance, right, where X is the amount of noise. So what we are saying, this formula gives us the probability of Laplace distribution, right, producing this amount of noise, right? And then if we set B to equal to lambda, and lambda is equal to GS, the global sensitivity of that query, divided by epsilon, then we said that this kind of mechanism that applies such noise is epsilon differentially private, right? So there are two things that governs the amount of noise that we are adding, right, to the answer. One thing is epsilon, which is a privacy budget, and the other is the global sensitivity. So what does global sensitivity mean? Really, it's the maximum difference. Sorry. So let me go back here. So global sensitivity mean the maximum difference, right, of the so the maximum value of the difference between applying the query on D and every neighboring database. Okay, so this is kind of the definition of a global sensitivity, and of course this is function dependent, right? What do I mean by function dependent? It depends on the function f, the query that we are asking. So we had an example here. If we have a count query, something like give me the number of individual salary greater than 30K, then we said that the global sensitivity is always equal to 1. Why is that? Because you see, if we started with this table, sorry about that. If we started with this table and then we remove the first column, right? So what is the global sensitivity between D and D prime? It's equal to what?
1.
1, right? Because previously in the whole table, the number of individuals salary greater than 30K is actually 1, 2, 3, right? But if we remove the first one, the first row, then we have only 2. So the difference between 3 and 2 is equal to 1. Similarly, if we remove the second row, then the global sensitivity is 0, and so on for the rest of the rows. If we take the max, that is equal to 1. So this is always the global sensitivity of count queries, which is equal to 1. Inshallah, you know, like in next class, when I go over the Python code, we will show you, or I'll show you a way to compute the the global sensitivity when it comes to differential privacy, or sorry, when it comes to any query. So that you can write your own query, write your own query, whether it be sum, mean, or whatever, and then you can compute the global sensitivity. Okay. So we said that this mechanism is called differentially private, right? And we call it Laplace mechanism. And simply, very simple, it's, you know, if we want to create a differentially private algorithm using Laplace mechanism, you just need to control the amount of noise that you're going to add by sampling the noise from a Laplace distribution with this parameter. Okay, so maybe the most challenging part is computing this GSF, global sensitivity. But if you have a count query, it's always 1, right? But sometimes you're going to be riddled with a more complex query, then you might need to think about it a little bit in order to come up with this global sensitivity. Other than that, it's very straightforward. Agree? Okay. So now we understand. You remember when the privacy, the value of epsilon, we said it has to be greater than 0 because of this constraint. If we have epsilon is equal to 0, right, then we have a problem here. We cannot add. Yes, so dividing by 0 is not actually a good idea. So that's why epsilon has to be greater than 0. So probably if epsilon is almost like as close as 0, that is the best thing in terms of privacy. However, if we are dividing 1 by this very small value, right, that's almost infinity, right? Well, that's almost a large number. So basically you are adding a large noise because the variance of the Laplace noise would be, or the Laplace distribution would be very wide, right? Because we have a large variance. So actually I'm adding up a large volume of noise. And that's why basically epsilon has to be chosen carefully such that, it achieves pretty good privacy, but it does not add more noise. Okay. So again, this question is an open question. And then I showed you a sketch of the proof. So I think, again, go ahead and look at it. To your own convenience. But basically, it's just a way that to show you. This is where differential privacy is really, why it's considered the mathematical proof. K-anonymization, the other mechanisms are really not that rigorous in terms of math, right? Right. And we had an example of count query, right? So if we want to make sure that this is a differentially private, then we just add a noise eta with this with this sensitivity, right? Or sorry, with this from this Laplace distribution, 1 over epsilon. And then we had kind of an example of if we have the sum, forget about the average, because maybe I'm going to ask you in the homework. So what is the sum? What is the sensitivity of the sum? And then actually, somebody said that because the maximum value that you can add in the age is b, then the sensitivity must be b, right? And think about it. So I'll leave this up to you again. So this is kind of the example. Now, up to this is, I think it was a review. Then I think we ended up in around this slide or so, where we are discussing the properties of differential privacy. And again, these properties were making differential privacy, dominating the landscape here. The first property, I think I went over this with you, so I'll just go over it very quickly. Post-processing meaning. Okay, I think I have a lag here. Post-processing meaning is that if you have a mechanism, right, that produces some outputs, and this output contains some noise. If you take this output and put it in another function, any arbitrary function, f, q, p, whatever, squaring, square rooting, then the output of that function, right, is still differentially private. More strongly, it's still epsilon differentially private. Make sense? So again, what I'm saying here is, I have a lag here. You see the slide?
Yes.
Okay. You see, if we have a mechanism A, right, that added some noise, and then we get that value and we square it, right? We square the value with noise, then this value is still epsilon differentially private. And that's what is called post-processing, right? So after the fact that we get this value, if we add it to another function, right? As I said, square it, cube it, square root it, whatever, the value is still epsilon differentially private. Okay. The other property that we are interested in is what is called the composability of differential privacy. And there are actually two compositions or two approaches for composition. Sequential composition, basically we have one database, which is D, And in this database, you are asking so many questions, so many queries. And each time, for each query, you will get an answer, right? And this answer is, let's say, is epsilon1 differentially private, epsilon2 differentially private, epsilon3 differentially private, and so on, right? So you remember in the patent privacy, when we talked about lecture 6, we said that, you know, like if the analyst of the is malicious and he's really smart, then whatever, you know, like whenever he send a query and get an answer, he then reconstruct some of the databases, right? Or that is some of the statistical information about the databases. What we are proving here is that in that settings, if we you know, like if we think about that setting, if we have a differential privacy mechanism for each query, right, then the output of all these queries, sequential queries, is still epsilon differentially private. How much epsilon? We're going to see in the next slide. Okay, and the other composition is the parallel composition. In other words, we're going to split the database into partitions: D1, D2, D3, and D4. Okay, and in each partition, and for each partition, we're going to run some queries, and this query is only going for that particular partition, right? So query 1 will go into D1, query 2 will go into D2, and so on, right? Even in this setup, it is still differentially private. We'll see how much. Okay, so let's talk about this this scenario. Okay, so let us consider the sequential composition first. Now, if for every query, right, we guarantee that it's epsilon. Sorry, for example, sorry. In query 1, we guarantee you that it's epsilon1 differentially private. For Q2, it's epsilon2 differentially private. In general, for any query I, we guarantee you that it is epsilon I differentially private, where, you know, E1 is different than E2 is different than E3, or it doesn't, you know, maybe or maybe not the same, right? So it might be the same, it might be different. Okay. So what do you think the total overall differential privacy budget, if we have this sequential composition? Any guess? Okay, so in other words, if we have a mechanism A, right? But this mechanism really does not ask one question, it will ask a set of queries. Query 1, query 2, query 3, all the way to query M, right? For each query, we're going to construct its own mechanism, A1, A2, and so on. So really, the randomized mechanism A consists of a sequential of randomized mechanism. So we're going to ask it sequentially, one after the other. First, we're going to use A1, then we're going to use A2, A3, and so on. But A1 itself is epsilon1 differentially private, epsilon2 differentially private, and so on. So what do you think that the differential privacy guarantee for the randomized mechanism A?
I guess the average of epsilon.
The average of epsilon. Anyone? Anyone else?
I think the least one of them, maybe.
The least one, okay. So we get some you know, like guesses, but I'm not sure if this is educated guesses or not. Think about it. If we have epsilon1, that is totally different than epsilon2, totally different than if we have randomized mechanism A1, that is independent from A2, independent from A3, and each randomized mechanism has its own epsilon, right? Epsilon 1, 2, 3, 4, and so on. The total mechanism, or the entire mechanism, right, is actually the sum of each epsilon. That is exactly what is the guarantees, the privacy budget for the entire A. So this is for A, right? It's not the average,
Sir,
it's not the minimum.
Sir, so
Yes.
that lowers the privacy?
That's lower the privacy, exactly. Because now, you know, if we start with epsilon, let's say epsilon1 is equal to 0.01, right? Where epsilon2, suppose that it's the same for the time being, sorry, 0.1. Again, it doesn't have to be the same, but you can have your own values, and so on. So suppose that we have 10 of them. So what is the summation of all this? So the summation
Epsilon 1.
is equal to 1. So now the privacy budget for the entire mechanism is actually 1 as compared to 0.1 for each sub-mechanism. And this makes sense, right? This makes sense because remember in the patent non-privacy, if we ask a question after the other, we'll gain more information, right? So the information will add up, right? So the privacy, what is the opposite of adding up? It will, it will adding down. So what I'm saying is that, the privacy will degrade because you are asking the one question after the other. The information with respect, the knowledge with respect to malicious is adding up, so the privacy is going down, and that's why the privacy budget is actually, going up. Make sense? I will prove it. If you are not still not convinced, I will prove it mathematically. But now, for the time being, intuitively, right? If you have so many mechanisms or like sequential mechanisms, the privacy budget for the mechanism A that sequentially combined all those sub-mechanisms is the summation of their epsilons. The same question I have for parallel composition. Again, in the parallel composition, we take this database, we cut it into partitions, and those partitions are non-overlapping. It has to be non-overlapping. And for in each partition, we are asking the query. And so we have a mechanism A1, that is epsilon 1 differentially private. We have epsilon 2, which is epsilon 2 differential privacy, and so on. We have A3, and we have A4. What do you think the privacy budget for A, where they, it's kind of running in parallel?
Out of the same epsilon.
What is that?
They have the same epsilon.
The maximum. And this is like what Hassan was saying. He was saying the minimum because he was. I think you meant maximum if you want to consider the worst case, but you said the minimum. So the worst case in terms of the parallel computation, the parallel processing for all DPs, right, is the one that kind of we will get it to take it for the privacy budget for A, right? So we have the max. Why is max is the worst case? Because if we have A1 that has epsilon 1 is equal to 0.1, where this, let's say, let's say 1 again, and this is let's say 2, where this is 0.01, right? Obviously, A3 has the largest privacy budget, right? So A has to bound to that number. A, the entire privacy mechanism has to bound to that number, because A3, right, is spending or is releasing as much information as, or put it this way, is exposing double the information that A1 and A2 is leaking or is exposing, right? Because the privacy budget that for A3 is double the privacy budget for A1 and A2. Make sense? So the output here is, okay, we can have some guarantees on the privacy budget if we are composing randomized mechanisms on top of each other. And there are two ways to compose randomized mechanisms: either sequentially, run one after the other, or in parallel. Partition the database into non-overlapping partitions and run the randomized mechanism, one for each non-overlapping partition. If we have a sequential one, then the overall differential privacy is actually the summation of the epsilons. If we have a parallel composition, the overall privacy budget is the maximum of their privacy budgets, right? So let's take an example, or let me prove you the sequential composability here, right? So again, we have A here, which is in the black, in the black square, that is composed of two different randomized mechanisms, A1 and A2, that runs on the same database, D. The first one is epsilon 1 differentially private, the other one is epsilon 2 differentially private. So how are we going to prove it? So let's use the definition. So what does the definition say? Probability of AD equals some value R divided by probability of AD bar equal to R should be less than or equal to e to the power epsilon, right? So I'm just using the definition. It is not clear. Let me write it again. Okay. So what I'm saying is probability of AD is equal to R divided by probability of AD bar is equal to R should be less than or equal to E epsilon, right? Make sense?
Yes.
Right. But remember that AD combined or is composed of two randomized mechanisms, A1 and A1 and A2, right? So I can write this as the following. Why is this not writing? Okay. Probability okay. So what I'm gonna do here is I'm gonna start breaking things up a little bit. So what I have here is the first mechanism will produce two numbers, right? One coming from A1 and one coming from A2. So it produces two numbers, R1 and R2. And so does the denominator. So we have A D prime is equal to, yeah, I think the battery of this. Anyways, so I'll just give up on this. Just I'm gonna go over the proof here. Okay, sorry about that. Okay, so here you go. Okay, can you see it?
Yes.
Okay, see in here, let me zoom in. Okay, see, so we have the probability of AD is equal to two values, one coming from A1 and one coming from A2. So R1 is coming from A1 and R2 is coming from A2, divided by probability of AD prime, producing the same values. However, I said that, you know, A1 and A2 are totally independent because they are sequential. They don't depend on each other, right? So what I can do here is, because remember in probability, if there are two events that are independent, then their probability is what? Is the multiplication, right?
Multiplication, yes.
Exactly. So we have, if we want to compute the probability, so I can basically multiply the probability of the first randomized mechanism getting R1 multiplied by the probability of the second randomized mechanism getting R2. So again, I'm breaking up A into its constituent mechanisms, A1 and A2. So multiplying their probabilities. Apply the definition, okay? Pretty much just like the Laplace mechanism, okay? So we'll get, because, you know, like if we split it into two terms, we have probability of A1 D equal to R1 divided by a probability of A1 D prime is equal to R1, and the same goes for A2. If we apply the proof in the Laplace mechanism, we'll get exponential epsilon 1, exponential epsilon 2, right? And you know that if we have e to the power x multiplied by e to the power y, so it's the final is e to the power x plus y, and that's why we have e to the power epsilon 1 plus epsilon to the power 2. Sorry, e to the power epsilon 1 plus epsilon 2. Make sense? So what I think that the only trick here is breaking up this probability into two independent probabilities, one coming from A1 and one coming from A2, and then apply that same proof for the Laplacian mechanism. Okay? So this is the proof of sequential composability. And as you see, we started with a fact definition, and we kind of added some properties and proved these properties using that fact, which is the definition. This is the nice thing about differential privacy. In other words, it allows us to, compose things pretty much just like building blocks, right? If we have, like building blocks, and we prove that this building block is true, then probably we can add up things in order to have a very complex system that is actually differentially private, right? And remember, having this post-processing, then the parallel composition and sequential composition, probably we can simulate any complex algorithm that we have. And in a minute, inshallah, in the next slide, I will show you that we can actually use differential privacy in 2 use cases. And those use cases, naturally, it has to be coming from the machine learning perspective, because what do we need? What do we want to do with data? The analyst, what does he need to do? Getting some statistical information, and we prove that average, sum, mean, whatever, they can be differential private, or they can apply some machine learning stuff, right? Supervised or unsupervised algorithms. One of the most used one is what is called k-means algorithm, and I'll explain it to you, right? So if we can use these building blocks, these properties, to build up a differentially private k-means clustering, right? Then we achieve our goal. We can say that, this k-means algorithm is actually differentially private, because we are using these properties: post-processing, sequential composition, parallel composition, and so on. And we already proved that sequential composition is differentially private, right? Just in here. So I might ask you to, in the homework, to prove parallel composability. Why it's actually differentially private, or why its budget is max EI, right? So I'm not expecting you to coming up with this proof from your own brains. I'm going to send you a link where it actually shows you the proof, right? But I want you to go over it, think about it, reason about it, right? And then type it or copy it in your own. Okay. So of course you can copy it, in a minute or so. But I want you to kind of process it and digest it in order to make sure that you actually why parallel composition is differentially private. Make sense? Okay. Right. Now you see, up to now we only talked about, again, we all talked about the Laplacian mechanism, but using queries just like count and sum and maybe average, right? Type. Using the property of sequential composition, can we build up some interesting application for differential privacy? Not interesting case, but I would say, can we use differential privacy for more complex use cases or applications? And the answer is yes, we can do it for building a private histogram or differentially private histogram. Now remember, what is really a histogram is? A histogram, if you remember in this slide, is nothing but we have buckets. Okay, I'll call it buckets or ranges, right? So this is kind of coming from the age, right? So basically, we're going to define an age range, let's say between 25 and 30, right? And we just want to compute the number of people that lay in this range, right? So probably what we can do is, in order to build a frequency histogram, first we need to define these ranges: 25 to 30, 30 to 35, 35 to 40, and so on. And then for each range, what should we do in order to get this number? What should we do?
Count the frequency.
We should count.
We should count, right? So if you are familiar with the database, what we can do is select something from a database where age is 25 and 30, right? Something like this, right? How many queries should we run in this case? So how many buckets do we have? We have 1, 2, 3, 4, 5, 6, and 7. So how many queries should we run?
7.
7 queries, right? Q1, Q2, Q3, and so on. Make sense? طيب. Using the properties of differential privacy. Using the properties of differential privacy. Can we do this in sequential or in parallel?
Sequential, sir.
Sequential. Okay. Anyone else? So okay, what I'm trying to say here is, right? Can we use the properties of sequential and parallel composition along with the way we're going to build a histogram in order to guess or know what is the privacy budget for building a differential privacy? So Yemen's saying it's sequential, right? So that is true because we're going to run this Q1, right? K times, or in this case, M times. So we're going to answer K queries, right? Right? K queries. So for each query, how much sensitivity should we add? 1 over epsilon, right? But we're going to run it K times, right? So overall, what is the maximum? What is the maximum amount of noise that we're going to add to the entire application here? Is K divided by epsilon, right? So this is kind of give you a way to build a frequency histogram. Basically, construct your queries, right? For each query, you add this amount of noise, K over epsilon. Make sense? Because each query, it should be parallel, right? It should be parallel composition, not sequential composition, Yemen. Because remember, what we're gonna do here is because each range, right? So we're gonna basically partition this database into non-overlapping region. Why? Because the amount of people between the number of rows between age 25 and 30 is completely independent from the people in the range of 30 to 35 and so on. So it looks like this. What is that? Let me go back to the parallel composition slide. So it looks like this, where D1 basically is coming from 25 to 30, 30 to 35, 35 to 40, and so on, right? And for each one, we're gonna add, or we're gonna run this count query. Make sense? So the count query, or the if we run this parallel queries on these queries all in parallel, then what is the maximum? What is the overall differential privacy budget that we get? Is the maximum, right?
But sir, don't you construct the histogram after you get your answer?
Yes, we do. So basically, what we're gonna
aren't you querying the same database then?
Right, but you see, you first of all you need to define your ranges, the age ranges, right?
Yes.
And then you're gonna ask this particular part of the database with this age range. How many people do you get? Right? And then he will answer you with the question, with the answer plus some noise.
Yes.
Okay. And that noise he has to add up some noise from a Laplace distribution with K over epsilon parameter. Right? Overall, if we get all the answers, so they will get an answer, we will build this histogram, right? And do for the next part and the third part until we get a full histogram, right? So probably you'll get something like this. So if you remember this slide, this is coming from think last slide or so, last lecture or so, you know, this is non-differentially private, right? And we saw that, you know, like by adding one guy, this histogram will be different by one unit. However, if we construct it in differentially private way, so this is what we get when we run the same histogram or the same query to build this frequency histogram is in this table. If we run it on the other table, we will get this kind of frequency histogram, right? If we run it again, we'll have a totally different frequency histogram, right? Because again, this process is randomized, right? So we will get different noises from one run to another. However, the probability of getting this frequency histogram and the probability of getting this histogram is bounded by epsilon, e to the power epsilon, right? So this is probability d, and this is probability d prime. If you know, like apply the differential privacy definition, then they are bounded by e to the power epsilon. No matter what, what does the frequency histogram looks like? Does it look like this, or really does it look like this? Obviously, you'll get a different answer from one run to another, right? But this run, if you compare it to another run, will be still differentially private. So now we use this parallel composition property in order to start with a count query and end up with what? A frequency histogram query. Right? So you are using this building blocks in order to make our use of differential privacy more interesting. And probably, if you are an analyst, you are more interested in, you know, like a kind of frequency histogram more than, let's say, just a count, a bare count. The last property, I think I got a question last time, you know, from the definition of differential privacy is that neighboring databases, you can only add or remove a single table, a single record, sorry, a single entry, right? So the neighboring database concept in differential privacy mandates you that you add or remove a single entry, right? And then you saw why. Basically because of the global sensitivity. The count query gonna be one. Can we construct a neighboring database by adding or removing more than one entry? That is exactly called group privacy, right? So now we're gonna relax this definition of neighboring database from being different by a single entry. Let's say by C records. So neighboring databases are different in C records. What do you think the global sensitivity will be? Huh?
Larger than neighboring databases.
What is that?
It should be C.
Larger.
Should be C, right? Because remember, if D and D prime differ in one entry, right? Then when we count, when we consider the global sensitivity of count queries, the global sensitivity is 1. Now, if the two neighboring databases, D and D prime, differ in C records, what's going to be the global sensitivity for the count queries? At most C, right? So in fact, if we have a group privacy, if we have a neighboring databases that differ in exactly C records, then we can apply the differential privacy definition where their probabilities between the D and D prime will be differed by e to the power C epsilon. Okay, and this is again another property that can be proven, but it's I'm gonna skip the proof, but because it's you know, like it's kind of straightforward. Now the question is, how if we start from differential privacy for a single record, how can we achieve this differential privacy for C records? In other words, how much budget should we allocate for each record, right? So that is kind of what we can discuss next, which is about the budget allocation. So this is kind of the end of this lecture. So I think so before start the next lecture, any questions? So just to summarize, what we covered so far is two things: how to achieve differential privacy using the Laplacian mechanism, and the other thing is what are the properties of differential privacy. And we talked about three properties: post-processing. In other words, if we take the value, the output of the randomized mechanism and put it in an arbitrary function, mathematical function, it's still epsilon differential privacy. And the second property is composability. If we compose a randomized mechanism, either in sequential or in parallel, we still can compute what is the overall differential privacy budget. And the third one is group privacy. We can relax this neighboring database concept from differing in one record to C records, but then the privacy budgets will jump from e to the power epsilon to e to the power c epsilon, right? So again, these are kind of, we use it as building blocks for differential privacy to kind of use it in more complex algorithms. Any questions? Sure. But it seems it is the effect of midterm exams, huh? So is it because of the midterm exams, or is it because of the concept is not clear?
Sorry, I say both.
اثنين.
I hope you can provide some number so we can
What is that?
the equation. Provide some number in the equation. Examples like this.
Which equation?
The last lecture.
Okay. So can you point to some slide exactly?
One above.
Okay, just a minute. You mean about the parallel and composite composition?
Yes.
Okay. 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 So what I think I can do here is, you know what? Maybe it will make more sense if we can cover example for parallel and sequential when I show you the code next class. Okay. Make sense? So I'll kind of manifest everything. So all this abstract notion and so on kind of will have concrete examples when we talk about when I show you how can we code, or how can we, you know, like use differential privacy in code. I'm gonna print, you know, use it in a very simple very simple database. Then we're gonna see how differential privacy will work. Make sense?
Yes.
At least we're gonna use at least the Laplacian mechanism. Okay. So I see the confusion here because it's mostly abstract. That's why, you know, like I'm gonna dedicate one class next class, inshallah, to kind of give you concrete examples on these concepts. Anyways, so far, so let me now the next slide, inshallah, we'll talk about one more mechanism to achieve differential privacy. But this mechanism is, you know, it's a little bit advanced. It's not really as easy as the Laplacian mechanism by adding one noise. No, it's a little bit. It has more, you know, like it has more. You know, like you have to be. It has to be a little bit involved in terms of guaranteeing the differential privacy. So that's why I'm just giving you as a concept. I'm not gonna ask you to prove it or anything. I just want you to know exactly where it is, why it's actually proposed, and why the Laplacian mechanism does not solve such issues, right? So that's why I just want to give you as a definition and as a concept. So far we talked about two models of differential privacy. Okay, so in the literature, when you go into, you know, like when you write lead articles, not necessarily research, but even, you know, like articles about differential privacy or so on, they usually talk about two models of differential privacy, or two modes of differential privacy: the global and the local. The Laplace mechanism is what is called a global differential privacy. Why is that? Because when we ask a question and we return with the answer with some noise, we need to compute what? What is this? What does this stand for? Ashar, what
Global
is
sensitivity.
global sensitivity? So what does the global sensitivity mean? Taking in consideration every neighboring database, right? In other words, we're going to remove every possible record in that database, and then we compute this sensitivity of the query. So basically what we're doing is we're going to look at the, like the full picture of the database, right? How really removing one tuple will change the output of this query, right? Not only one tuple, every tuples. So it will give you a global picture, a big picture. That's what is called a global differential privacy. On the other hand, we used, remember we talked about the randomized response, right? So in a sense, we said that randomized response is actually differentially private. And we had some, controversy in terms of defining what is a neighboring database, and it's a little bit different setup. Yes, because this setup is called local differentially private. In other words, what is going on here is the query, the analyst is asking a question to the database, and the database consider it as untrusted. He will, ask every particular guy in this database, give me your answer, adding it some noise without telling me how much is that. Or in other words, each user will flip a coin twice and so on, right? Remember that's randomized response. He will flip the first coin. If he is a tail, he'll say honestly. If it is a head, he will flip another coin, say yes if it is head, say no if it is tail, right? And he will report the answer to the database. Suppose that there is someone sitting in the database to kind of facilitate this operation. Now, the noise that has been added to the answer is computed by each guy locally. So N1 is different than N2 is different than N3, right? Because each one will flip the coin by himself, although the same process, but the output is independent from each other. Unlike the global differential privacy, because we have, if we remove one tuple, that will affect the overall answer, right? So this is kind of the difference between global and local. So global, as I mentioned, considering all, like adding one tuple or removing one tuple will affect the overall answer for the query. On the other hand, local, right? Each user or the noise that is added for each user is different than the other. That's why it's called local. Okay, so we know this, like we have covered this, but without giving you this terminology of global and local. So I thought this, I'll give you kind of a heads up. Anyways, this is, it's not really necessarily, but I thought that, like if you want, just to avoid confusion, we'll go read other sources. You don't know what is global and what is local. So this is kind of common terminology. Let's talk about another differential privacy mechanism. But in this mechanism, remember, in Laplace mechanism, or so far, we are asking all the queries that we are asking returns a real number, right? If we talk about sum, we talk about an average, we talk about a count. Make sense? Somebody asked me, how about if we have a more specific question, right? For example, if we are asking about, let's say, the highest range in this group, or sorry, what is the most frequent range in your group, in the class? Sorry, what is the most frequent age, right? In the group. It is a real number. Make it more generalized. What is the most taken class, right? What is the most taken course, right, among the students in this class? Let's say, for example, ICS 440, because most of your concentration area. So you're not asking about a real number. You are asking about what? About a category or about a specific item in the database. Is that clear? So the type of question that you are asking is different. Not necessarily you are returning a real number. I'll try to make it more generic. Suppose that we have a database. Okay, and this database has entries. So entry 1, 2, 3, 4. Suppose they are students, whatever. And you are asking a query, function f. This function f is mapping each entry to some output, right? So it's mapping this blue rectangle to a blue triangle, and mapping all the these two rectangles into this triangle. So what I'm trying to do here is I'm setting up a new function f that doesn't really necessarily give you a real number, but it kind of map an input to output. Okay, so think about this function as a map between an input and output, where input is the entries in your database, and output is whatever interesting outcome that you are looking for. What is the most common course in among your section? What is the let's say the most visited building by students in this section? What is the most language spoken by student in this section? All kind of whatever kind of question that you think about, right? And why we are making it more too generic? Because like when we apply it to algorithms, we need to map this algorithm that we have in hand, the problem that we have in mind, to this function. So again, here is an example. What is the common second language in this class, right? So for example, this can be English, Spanish, French, whatever, right? And then we map students to his most common to his common language. And this mapping is done by this function f. Okay. Now, obviously, this f does not return a real number, so we cannot add a noise from Laplacian distribution. So the question is how to construct the differentially private version of it. And the answer is we have a way, which is called exponential mechanism. And this is the most important thing about this exponential mechanism, is where does it apply? Okay, where does it apply? And the answer to that, it applies to cases or to scenarios or settings that Laplacian mechanism cannot work, obviously, which is if we have a function that does not give a real number. It gives what? It gives one out of some set of outputs. So these are the outputs, right? So let us put things a little bit formally. Suppose that we have what is called a scoring function. Okay. Do you see the slide? Okay. Do you see the slide I'm having now?
Yes.
Okay, here you go. Assume that we have a scoring function W. This, just like any mathematical function, it will take a range. Sorry, it will take a values from a domain and produces a range. And suppose that this function takes two inputs, D and O, where D is the set of all possible databases, right? Just like what we would discuss in the definition of differential privacy. Think about any possible database, which is D, and O is the set of all possible outputs, right? We might construct out of this function, and it produces a real number R. So this is a scoring function, a bare scoring function. Okay. So what does the scoring function does is as the following. Okay. Or before what it does, let me give you an example. Suppose that the database is, we have a one big table, right? That considers that has, a number of people, and this column has the nationalities of all these people, right? So it's basically the nationalities. Now, if we define a function called #dr, basically what we are trying to do here is we want to count the number of people, right, in this database that has nationality R, exactly nationality R. So we call it this function, right? So this is a function. And suppose that FD is the most frequent nationality in D. For example, in our case, Saudis, right? So we have FD is the most frequent nationality. So this scoring function, right, basically will map, okay, the people in this database with, let's say, this output, particular output, and give a number. right? Let's say a score. Sorry, we'll call it score. And this score is nothing but the difference between the number of people, right, that has some nationality R minus the number of people that has the most frequent nationality. So just to be concrete, suppose that, you know, like the most frequent nationality is Saudis. Suppose we have 33, right? Suppose that, let's say it's 20, right? And we are asking about nationalities, let's say, coming from Egypt. Okay, so number of those students coming from Egypt, let's say, is 5. Okay, so what is the scoring function? Basically, it's going to be 5 minus 20, right? So that is what? 15. So 15 is the score. Of the nationality of Egypt. In other words, we have a database here, right? And here we have all the outputs. And the outputs basically are countries or nationalities. Let's say we have Egypt, let's say Lebanon, let's say Syria, Jordan, and we have obviously Saudi Arabia, right? And then we're going to map, right? We're going to map these databases with each nationality. And these databases coming from what? Students. So this edge will have some score. So this score is 15. Let's say this score is 10, and so on. So this is the scoring function. Basically, it will score. It will give kind of a score, right, to the database with respect to each output, each possible output. Why I'm explaining this? Why I'm explaining this is to have a way, right? A way to connect D with R. So we have D here, set of databases, and we have the output, all possible output. So we want a way to connect D and R, just like in the previous slide. If we have a way to connect the input to the output, then we can come up with the sensitivity function, W. The sensitivity W of this scoring function W is nothing but the max for every output and for every neighboring database, differing exactly one output, and the difference is between their scoring functions, right? Okay, so this is basically to delta W. And again, this is one of the slides that you need to think about it carefully, right? So I'll go over it next time, but please go over it before Tuesday. Make sure that you understand, articulate some questions, and maybe we can answer it. What is the conclusion here? The takeaway message here is, again, you see, even for this kind of setup of question, what is the second common language in this class, we need a sensitivity function. In this case, we took all this detour in order to formulate a scoring function. And then we have, you know, like this is a kind of definition of our scoring function. And then we come up with a sensitivity, delta W. What we're going to do is we're going to use it, okay, this delta W, in order to prove, right, that we're going to have a mechanism A such that the probability of ADR, if the probability of ADR is drawn from an exponential mechanism, right, or an exponential distribution. And exponential distribution always take what? A mean. If you go into, you know, like your statistical course, exponential mechanism always look like this, e to the power minus lambda. So this is exponential distribution. So if we, again, just like Laplacian distribution, if we take lambda and be it as a function, sorry, if we take lambda as a function of epsilon and GSF, right, pretty much like we're doing here, then we'll have a differential privacy mechanism. Okay, so in other words, what is the point here is, so if we have a mechanism A that is set to answer such a question, which is about the most common language, the most common course, or so on, if the probability of sampling that output is proportional to the exponential mechanism with the mean being epsilon multiplied by WDR over 2 multiplied by the sensitivity of that function, then we have differentially private mechanism. Okay, and the intuition here is that if we want to pick the, if we are asking about an output, and we want to pick the mostly likely output, right? That the probability of picking that value or that output should be proportional to the two things, to epsilon, which is in this case here, and its sensitivity, delta W, right? So this is basically the intuition of exponential mechanism. And again, it's a little bit not straightforward to understand. I think what is the takeaway message here is, so this is, maybe this slide is just for, to show you the complexity of it. The takeaway message here that I want to convey is that where should we use exponential mechanism, right? Because in real application, most of the time, we're not only asking about average and mean and sum and so on. We need to ask about arbitrary questions, right? Pretty much, what is the most common language in the class? This is not, probably the answer is not a number. It's a very arbitrary question. Right? The question is, can we answer this question using differential privacy? And the answer is yes, by using this exponential mechanism. And as I told you from the beginning, it's not straightforward to understand, right? So that's why I think this is the most important slide here in this lecture. And what follows is just like a way to set up the exponential mechanism, right? So therefore, this should not be included in the exam. It's not fair to ask you to kind of understand how to construct this exponential mechanism and so on. So this is not included in the exam, neither the quiz. This is just for your information, okay? And the reason that I'm adding it here is just to show you that differential privacy really the researchers behind differential privacy, they consider generic cases, right? Not only average and mean and sum and so on. They consider really generic cases where anyone can ask any question, really, any arbitrary question. But in order to model this arbitrary question, we have to go through this mess, right? So we have to understand what is a scoring function, how to construct it, what is its sensitivity, and then, computing this probability. We have a proof. It's actually differentially private, and this is called, this mechanism is called exponential mechanism. So again, this is not included, neither the following slide. Make sense? So the most important slide that I want you to really digest and understand why are we doing this is, where are we applying the exponential mechanism? So I'll stop here. I think we have only 2 more minutes. I'll stop here, and inshallah next time we will wrap up this set of slides. Basically, the coming set of slides is kind of an application or use cases of differential privacy. So I'm going to cover some interesting case called max response, where basically we're not asking about how much, what is the maximum, where we are asking about who got the maximum votes, for example, who got the maximum score, okay? And again, we're going to prove that it's differentially private. The other one, for those who are interested in artificial intelligence or machine learning, we're going to show you that k-means problem can be actually differentially private, right? By just, adding some noise, adding some noise at certain steps in k-means, and we will, assure you that this is differentially private. But just to be more, complete, I'll show you, for those who are not familiar with k-means, I will go over the k-means algorithm. And the final one, the final application, is in the what is that called, Netflix prediction. Remember, Netflix prize was one of the issues that we came up with k-anonymization, right? So it might be also logical to think about how applying differential privacy in that setting, really, to solve the problem, or the privacy problem that arose from the Netflix competition. And then we're going to boil it down into, where actually we are applying the noise on, And again, I'm not going to go into the details because, again, devil in the details. I'm just going to give you the full picture, right? And I think we'll talk about some challenges in differential privacy. So I think what slide number 9 really is, I'm not gonna, like it's really about convincing you that differential privacy is generic, that it can be applied in almost any algorithm that is being used to produce some certain some useful information. And I'll stop here. So thank you, and shall see you next Tuesday. Don't forget the quiz, inshallah. Any questions?
Thank you, sir. See you next week. See you next week.
And again, you see, I mean, Osama, you were concerned about students. You want some concrete examples. I will do, inshallah. But it makes more. It will be more interactive and more kind of, let's say, not